So in this video we are going to discuss about the thermal resistance. See, when two physical systems are described by similar equations and have similar boundary conditions, these are said to be analogous. See, the transfer process may be compared in analogy with the flow of electricity in an electrical resistance. See, let us take Ohm's law. See, this Ohm's law states that the current is directly proportional to the potential difference. So, I is directly proportional to dV. Whereas, when we take the Fourier's law, it states that heat transferred is directly proportional to the temperature gradient, or you can write heat transferred is equal to T1 minus T2 by L by Ka. See here, in order to remove this proportionality, I is equal to dV by R, we can consider. Here, the resistance offered is the electrical resistance to the flow of electrons, whereas here in the Fourier's law, the resistance that is offered to the flow of heat, that's why this resistance we call it as the thermal resistance, and as this happens in the conduction, we call it as thermal resistance due to conduction. Whereas if you take Newton's law of cooling, so here Q is equal to Ts minus T infinity by 1 by HA, where this 1 by HA is the convective thermal resistance, RTH convection. See, Ohm's law and Fourier's law are analogous. Ohm's law and Newton's law are analogous because they have got the similar boundary conditions. So that's why they can be said to be analogous. Now, when it comes to radiation, so heat transferred by radiation Q 1 to 2 is equal to T1 minus T2 by 1 by sigma A1 capital F1 to 2 small f1 to 2 into T1 plus T2 multiplied by T1 square plus T2 square. This total denominator term we call it as the thermal resistance due to radiation. See, this thermal resistance plays a very important role in heat transfer because heat transferred is simply written as the temperature difference by the overall resistance. So temperature difference by overall resistance you can consider, and the reciprocal of thermal resistance we call it as thermal conductance. So reciprocal of thermal resistance is called the thermal conductance, and here it may also be noted that the rules for combining electrical resistances in series and parallel also apply equally well to the thermal resistances. So that means if you take resistances in series, see, there are two resistors like this which are connected in series. This is R1 and this is R2 resistance. Then the total resistance sigma RTH when they are connected in series will be R1 plus R2. And when we take resistances in parallel, now you can see the two resistances are connected in parallel like this. So this is R1, this is R2. Then the equivalent resistance will be given by 1 by Re is equal to 1 by R1 plus 1 by R2. So from this 1 by Re will be equal to, if we take LCM, R1 R2, and this is R1 plus R2, and therefore Re will be equal to R1 R2 by R1 plus R2. See, these two formulas stand good when we take thermal resistance also. Now, how do we represent this thermal resistance? Suppose, let us consider there is a plain wall like this. One side of the wall is at temperature T1, the other side is at temperature T2. If T1 is greater than T2, heat flows in this particular direction, and you can consider this as the thickness L. Now, this same diagram can be represented in the form of an resistor like this. Here, this side is at temperature T1 and here it is at temperature T2. Heat is flowing in this direction. So, the resistance RTH, the thermal resistance, is here nothing but L by Ka, where K is the thermal conductivity, as earlier we have discussed. And here, remember, the unit of thermal resistance will be always Kelvin per watt or degree centigrade per watt. So, that depends upon whether we are considering the temperatures in degree centigrade or in Kelvin here.